All right, welcome everyone to another OCP Top Call. This is call number 143, calling you from Ottawa, and we are in this in ISPCS 2025, and today's call, like we have Philip. It's my pleasure to introduce Philip, Senior Space System Engineer at Planet Labs PBC, where he specializes in satellite and mission operations. Philip is also a fellow at the Open Lunar Foundation, where he led and pioneering like the research on timekeeping for lunar mission, and he serves on the Senate at the MoonDAO, contributing to community-led space development initiatives. In today's talk, titled Prototyping a Low-Cost CSAC-Based Time Card for Lunar CubeSat Mission, Philip will share his work, how commercially atomic clock technology can make precise timekeeping accessible to small-scaled and university-led space missions. His project demonstrates that affordable chip-scale atomic clocks, also known as CSACs, could bridge the performance cost gap, enabling the next generation CubeSat missions to participate in building the cislunar timing infrastructure. So please join me welcoming Philip. And I will actually give Philip my laptop, and because he's sitting right beside me, and I will just share, let's see, share the screen first, and we'll take it from there. So share screen and share, and I don't know if we can make it full screen, but I think that should be good enough. Yeah. Okay, Philip, here, the floor is yours. My laptop is yours. And then just, we'll make sure, please, everyone mute your mic so we don't have hiccups in middle of the presentation. Let's see. Where is that? I don't know where that is. So if everyone kindly just mute, then we should be good. Okay, Philip, you take it from here.
Thanks. Can everyone hear me okay? Just the thumbs up reaction would be fine.
Yeah. Maybe someone unmute and say yes, you can hear. Okay, perfect.
Hey,
thank you.
Thanks, Paul. So hello, thanks for the introduction, Hamad. I'll be presenting the low-cost CSAC-based time card for lunar missions. That is a senior design project for students at Rochester Institute of Technology this past year. Open Lunar Foundation, which I'm a fellow of, sponsored the project, and MoonDAO, a decentralized autonomous organization that is the Internet Space Program, used a community vote to put grassroots funding together and buy the actual oscillator. So I'll be presenting on behalf of my co-lead, Ashley Kosak, and the RIT team, which has too many names for me to read out right now, but you can see them here at the bottom of the screen. And thank you. Okay, so to set the scene here and why we're doing this, Open Lunar Foundation has recognized that infrastructure at the moon is lacking in terms of it's not existent right now, but the presence of infrastructure and shared infrastructure at the moon is a big deal, and it's difficult. So if you open your phone and you turn on GPS or open a map app, you can get your location to precision, like within a couple meters instantly, or get the time from the GPS system to within nanoseconds of UTC, anywhere on Earth. That's awesome. The moon is pretty far away, and the GPS signals from the moon are actually detected at the moon are extremely weak. So combined with the weak GPS signal and the fact that it takes 1.5 seconds or so for a photon to go from Earth to the moon, there really is a need for a local standard for lunar time, or perhaps an ecosystem of time appliances at the moon that can manage the infrastructure and relate back to Earth in a more distributed way. And so what we were looking at here on the premise for the project was to take that from millions of dollars to tens of thousands of dollars, as I'll explain here. So physically speaking, moon time and Earth time are different. The moon and the Earth, like if you had ideal identical clocks on the surface of each, because physics, the one at the moon will be 56 microseconds faster per day. And if you're using GPS, and which depends on time of flight for the signals that you're measuring, like if we use time of flight for the timing, like 56 microseconds over a day is kilometers of navigation error. So we need something better. We need something. Open Lunar and MoonDAO are committed to open access. One of the things that could happen in the future are fractured PNT systems built by and maintained by different actors who may be at odds with each other or keeping technology proprietary. And while this is okay for an ecosystem and an economy, timing is at the foundation of every mission. It's the foundation of wireless communications and navigation, and pretty much everything else. If you go deep enough, it all depends on time. So the idea of having fractured systems, multiple lunar coordinated times that could be out of sync with each other or not coordinated or closed is a real risk. And having an open access baseline is key to just encourage peace, cooperation, and accountability for the future, set the precedent. Okay, so we want to put a clock there. We looked up what clocks do we have. Quartz oscillators, crystal oscillators are great at the short time scale. For everyday electronics, totally okay. Atomic clocks are stable for longer. Chip scale atomic clocks, which we'll talk about today, are better, but not the best. And then NASA has shown that deep space atomic clock can stay accurate to within nanoseconds for years on end at the cost of $1 gajillion, right? But how hard could it be? Let's figure it out. Not too bad, right? Unfortunately, it's like the worst case scenario for any space design or space mission. The speed of light means the speed of light is 3 × 10⁸ meters per second, right? And it's constant because of general relativity. Practical applications of PNT require, at best a meter of uncertainty or more, or better in position data. So if you do the math just to convert how long it takes a photon to travel 1 meter, it's 30 nanoseconds. And that kind of sets our uncertainty goal. And then, because we're at the moon, lunar assets can go days or weeks without line of sight to Earth if they're, let's say, at the equator and on the far side of the moon, or at the mercy of schedule, where a lunar reconnaissance orbiter will relay the message back to Earth, but it can only relay so many messages at once, and those systems are already oversubscribed. So that sets kind of how much we're targeting for the holdover of those clocks. Let's see. Sorry. So yeah, the deep space atomic clock is awesome. It's so stable. It's
I sent you the wrong presentation. Sorry.
It's okay. So the deep space atomic clock, brilliant. Love it. It was exquisite technology. It was characterized extremely well by the scientists and mission operators at NASA. And if I didn't have constraints, I would want everyone to have access to time from something like the Deep Space Atomic Clock. But I like chip scale atomic clocks. You know, they're good enough, right? They're less than $10,000. They sip power at 120 milliwatts, and they can be stable over the interval of days. So, sorry, I keep clicking the wrong thing here. So the question is, are the CSACs good enough for our space operations? And the answer is, you know, maybe. The students here did a simulation to see what it would look like to have a clock run for 14 days and see how close it is to the actual time. And it's just not physically possible, even with an ideal, perfect chip scale atomic clock, to achieve that 30 nanosecond specification. Even if, yeah, you discount all noise, all aging effects and everything like that. So we have to think of it a different way. How precise and accurate could a CSAC take us for $5,000? The students put together a model and for the clocks and put in the specs from Microchip's datasheet. And they SI's datasheet for their clock. Ran the numbers to see theoretically how good could it be. So this is where we came in. Open Lunar is a nonprofit and who I'm speaking for here today. And then RIT, the Rochester Institute of Technology, is in my hometown of Rochester, New York, and has this program where it's engineering students are required to take a capstone course, but they're given free rein essentially over an entire project. So Open Lunar invested in this RIT program for young professionals who are about to enter the workforce with MoonDAO. MoonDAO is the Internet Space Program. It's an organization that's a grassroots community with Treasury that only spends money if it's voted to do so by the entire body. It uses blockchain to do the governance structures. And MoonDAO's ambitious goal is to celebrate New Year's Eve on the moon in 2030. So with MoonDAO's enthusiasm and ability to buy this oscillator, we could start thinking about how we would use it. And so we went open source. We love open source. This is, you know, how basic technologies can proliferate here. And there's an ideal reference to start from. We don't have to design it from scratch. The time card provides us the perfect blueprint. And y'all are familiar with the time card, so I won't go into too much detail there. So this is the clock we have. And it's a 16 megahertz clock. The manufacturer claims it's space rated. I won't read all the stats here, you know, you can come back to it later. And here's a picture of what it looks like on the dev board when we did a lot of the testing. So to put it on a satellite, what's the interface look like? We're building the time card. So we're building the thing on the left and designing it in a way that would be representative to hook into a small satellite. The card itself, this is the block diagram, obviously inspired by the time card. So the student's design uses temperature-controlled crystal oscillator that drives a phased lock loop that they wrote themselves to steer the chip-scale atomic clock. And there's a GNSS antenna that gets the time from GPS as the reference. And then for our testing, we'll turn it off and see how the drift can be characterized. So the students design their own phase lock loop. I'll be honest, I understand controls, but this is not my expertise right now. So I'll do my best to answer questions. But that phase lock loop was implemented on an FPGA. And then the students modeled it all in Simulink including noise sources and aging factors. And here's what the model and the data sheet show. So the red is what the data sheet claims, microchip claims. And then our model here is close up until very precise, very small time intervals, which is due to some of the filtering and other assumptions that were made in the model. So we can't really use that stuff to the left, but it's okay for what we're looking at, which is, on the days scale. So the test itself, we looked a bit like this. There was a Raspberry Pi with a GNSS antenna, and it was acting as the satellite, the server. The MSP-430 is basically the satellite's flight computer in this scenario. And then the CSAC is there in the middle. The desktop computer and the Raspberry Pi and the MSP-430 are all recording telemetry. So we can, when the GNSS switch was open, the students watched what happened. And obviously, I'm sure most of you aren't surprised by this, but it's temperature dependent. And so this was a discovery for the students. They didn't realize how significant temperature control would be. This was tested in ambient conditions for a number of days. And looking at the data on the according to like the shorter time scales and comparing it to the data sheet, our measurements are not great, right? Not super precise, but they're pretty close to the data sheet. So that gave us good confidence. The students went ahead and assembled it on a PCB, and I have that here today. This is the board in a 3D printed CubeSat frame. So this frame is built to the CubeSat spec for what the entire satellite bus would be. There's plenty of space on this board. It could be much more compact. And that just goes to show that this is entirely possible to fit in size, weight, and power on a CubeSat. So my idea here is CubeSats in 1999 were a project from Cal Poly that was more of an idea than anything of, hey, let's make this simple enough that someone could pull something off the shelf and be ready right away and have confidence that they could succeed in making a low Earth orbit satellite. NASA gets involved, it builds legitimacy, and then by the 2010s, there are commercial companies deploying hundreds of CubeSats for legitimate production operations. And today, students in college are spacecraft engineers by the time they graduate with on-orbit experience because of the CubeSats they have in their programs. So it's an extremely accessible way to approach satellite engineering. And so I'm thinking, okay, there's a lot of similarities here, right? Sorry, here's the stats. I'll skip that. I'm going to flip back and forth between these two slides, right? Could time cards do the same thing that CubeSats did for low Earth orbit satellites? Well, they're cheaper than the exquisite professionals. They're accessible to universities. They use commercial off-the-shelf components, standardized form factor, rapid development cycles. If you lose one, it's fine, and it's the students at the college level can train and enter the workforce with expertise. Actually, it's pretty much the same thing, right? For a time card, much cheaper than the like professional grade exquisite solutions. COTS components, cheap enough to build in a university, rapid development cycles. And both of them are open source to where you can build it. You don't have to build it to a standard. You can make your own flavor and customize it to your needs or to test novel solutions, right? So that's where I'm headed. Open Lunar's timekeeping project we intend to continue this question, keep asking this question, keep getting more students involved. iterating on the hardware to eventually flight qualify it to go on a CubeSat. So it won't look like the one that's here today, but eventually, hopefully within just a couple of years, we'll have a board made of fully commercial off-the-shelf components that are accessible. You can just buy them and assemble them in a university and fly it on orbit. We'll learn a lot along the way to make that better. But there's another problem, right? That clock wasn't good enough, but we can use ensembles of clocks, many clocks, in concert to improve the stability and reliability of that output timing signal. And that's more of like a software and a system level architecture problem, not the hardware problem that we saw before. So both of these can work in parallel. And then the last piece of this here that brings in the moon is coordinated lunar time, the time card project, and LunaNet, which is NASA's common specification for communications and the lunar internet, as it were, so everybody can communicate with each other, right? And so that discussion is already happening in a lot of professional circles, and we're there, right? So we're keeping track and commenting on things that are doable, things that are not doable, learning, and also making sure that the flight qualification and ensembles and everything are meeting that bottom baseline needed for interoperable lunar time. These are the folks that made it happen. From Open Lunar Foundation, my co-lead, Ashley Kosak, and then I was on the project on behalf of MoonDAO. And here's the students from RIT: Eva Zuckerman, Ian Dolphy, Nisada Muyinda, Drew Shack, Luke Schramm, and Tanner Smith, posing there with the clock. That was such a proud moment for me, bringing the clock there in person and getting to hand deliver it. So there's some references here. And I do have some backup slides if you want to get into the weeds. But that's all I have prepared for the presentation so far. So thank you. I'd love to take some questions if anyone's curious. There's a lot in my brain that hasn't made it to the page yet. So I'm here at the IEEE Symposium for Clock Synchronization and learning a lot more. And I think the next iteration of this I know the next iteration of this project will be a leap forward in not only performance, but the premise of college students entering a niche field with expertise already. And that expertise is required for lunar operations, deep space internet, the solar system internet are all part of these foundations. So there's potential here.
So thank you for your presentation. One question I had is, for the OCP NIC to be used in this, would it have to be rad hard? In other words, ready to use in space, industrial or military, time, or not time, temperature sensitive? Or
yeah, I mean, the answer is yes, you should and could, but don't have to. One of the reasons why we want to take this concept sort of to the extreme and push it and see what we can get away with and still have it be usable. So our objective is a usable result, not the best or a good result. Because these devices are so cheap, they're throwaway. The CubeSat philosophy here is that we can try and fail and try on orbit, measuring what happens. And in my experience in satellite operations, the components today and with the conditions in space, it's a lot more resilient than I imagined. And the problems that are really scary on paper don't really matter that much because day to day, depending on the application. So the military or science, NIST wouldn't be using these, right? Or they would hopefully be using something better. But in order to get to the moon and set up that infrastructure, it would be great to have this baseline already there to build from.
Got it. Thank you very much.
Yeah. One thing I'm also hoping to learn from this project is really what it takes or what unlocks that PNT infrastructure at the lower level for accessibility reasons. Lots of times, especially in PNT and timing, there's this, I don't know if it's real, but it appears to be a huge barrier to entry professionally, not only because you need a good body of expertise to have those conversations about the fundamentals, but also because there's legacy of decades of hard work and innovation and measurement that builds up all of this stuff that kind of happened in the background, in my opinion, from my perspective. And so to catch people up to talk to about this, if they're outside of the industry, is difficult. But also for me, I'm kind of in the middle, right? It's hard to ask the right questions. So in addition to, we love to work with the different oscillator companies, or if you'd like to test your PLL, or you'd like to help us make a flight ready or flight qualifiable time card, please get in touch. We're looking for subject matter experts and advisors. So not just the advisors to the hardware and to know what components to do or know what requirements to set, but sort of mentorship on the philosophies that go behind these things, the intuitions, so we can build that up, build that in, and include that as part of this accessibility endeavor. Any other questions? Anyone have questions about the hardware or the simulation? I'll go back to some of the more dense slides so we can take it all in. One thing I'm learning here at this event for clock synchronization is that a CSAC might not be the answer. There are other technologies for oscillators, and finding out which one has that sweet spot of performance, resilience, and stability, especially in the space environment. It's uncharted territory, not uncharted, but there's room for exploration there. The space environment, for example, is obviously the radiation. So the solar radiation, high energy particles from the sun can cause bit flips and charges that build up on the hardware. If you don't account for it, it can fry your equipment or corrupt your firmware. So satellites, like satellite integrators, know this, and they build it in to the systems to recover from such things. But what if that happens for a time appliance? Can the system recover and stay resilient? That's an open question. Also, obviously, temperature control. honestly, it's a lot easier to do temperature control in space, in my opinion, because you only have to worry about radiation. You don't have to worry about and conduction, and you can yeah, it's harder to dump the heat though. It's harder for the heat to find some place to go. But I'm not a thermal engineer, so if you know one, don't tell him I said that. Yeah, any folks? Yeah, there's if there are no more questions, is there anyone to run the meeting on behalf of Ahmad? Maybe we call it.
Okay, I can call to end. Well, thanks everyone for attending. And
Thank you so much. Bye-bye.
bye.